Okay, so we're gonna get back to what we were doing. So step one finish. All right. So I think we understand that step one finish. So we're gonna go to step two now. Okay, let me just present. All right. So what does step two have in store for us, right? So step two now is actually using our Friedel-Crafts catalyst, right? Um, as a way to introduce our electrophile, right? So step two is our electrophilic attack. Electrophilic attack, right? I am not able to write on this thing properly, right? So electrophilic attack. So what we're gonna have now is our benzene ring. So let's look at benzene and draw it large and pretty, and let's put the double bond there. All right. So what we're gonna have now is it's being attacked by this entire complex here. And yes, you have to draw out all of this. So this is step two, right? So we have this here now. Now where we have the ability, since it has a slightly positive charge now, and here's a slightly negative charge now, now we have the possibility of electrophilic attack. Both two electrons move from that double bond right there. Excess electrons move on there. Make sense?
So can you go from where the electrons move from the double bond
All
from
right.
right there?
So we know that the double bonds are high electron systems, right? So what we're gonna have is two electrons, right? We remember we need to form the bond, we need to form the carbon bromine bond. And bonds take two electrons. So two electrons from here, let's say that two electrons are here. Both of them collectively are shown by a full arrow. So electrons go towards the bromine there, and electrons in this bond here goes towards that bromine there. Make sense?
Okay, yeah.
Lovely. What is our product? Let me draw the product down here. If the screen gets too messy, just let me know when I need to clean it and show what's happening, right? What we have now is the addition. Let me not draw it like that. I'm talking about molecular geometry here. So let's show what we have now. We're gonna have something like this now. We're gonna have bromine and we're gonna have the hydrogen there. We know that each corner of the benzene has a hydrogen, right? We knew that,
Yes,
right?
sir.
Okay, we knew that. Just making sure we knew that. Um, okay. So what we have now, what I'm trying to explain now, is that this carbon here is where the benzene added, is where the bromine added, This carbon here is sp2 hybridized. But when we add a third group to it, a fourth group to it now, this is now sp3 hybridized. What it does now, it breaks the hyperconjugation of the ring. So we have a positive charge. And what will happen now is that we're going to have movements, right, of electrons throughout the ring. We're going to have, let me just be R, H, positive charge, right? So we're gonna have the display of multiple conjugates. Hoping you guys can see that and understand what I'm talking about. The positive charge will now move around the ring, continuously move around the ring until it is stabilized. Make sense? So all of these are unstable intermediates. And that is because the carbon is sp3 hybridized. What Huckel was saying, is that our carbons must be sp2 hybridized. They must be flat. They must be planar. In this case, they are not planar. Because if you look at the carbon before, sp2, this is planar. 190, 190, 190 degrees. Right? Not 190, 109. Sorry about that. 109, right? Degrees around. But what happens when you add a third group to the species now? We're going to have a tetrahedral structure. It's going to break our perception. We're going to have carbon here, and we're going to have something like this happening. Right? We're going to have something like this happening, right? Where we're going to have this type of structure where this is where on top of it is going to be 109 and then around is going to be 170. Is going to create a bulky structure and that's going to break aromaticity. The rule of aromaticity states what? The second rule must be sp2 hybridized. Once we add the electrophile, it breaks it. It becomes sp3 hybridized and break the stability of the ring. That's why we have the formation of unstable intermediates. Following so far, guys?
Yes, sir.
All right. What we have left is FeBr4. Okay, give me a second, guys. Sorry about that.